Hello, Sendoff. We continue our how-to, and this time we shall talk about bricking an expensive device. Yeah, thank you very much, and I am going to share with you a very real case. The case of rise, fall, a lot of fear, and ultimate success with bricking, obviously. We have already mentioned that PLCs are usually connected to the network, and network is filled with switches. In industrial enterprises, you usually use industrial switches, which means that just like the PLCs, they're expected to operate in a very reliable manner despite the pretty aggressive environment they may be used in. Lots of network devices have a firmware very similar to the firmware of a PLC. They are running usually a monolithic operating system. In most cases, they don't really have file systems. All they use is tasks. So, if there is an error in one place, the whole PLC will usually crash. So a particular device I'm talking about came from a very well-known vendor. It cost $5,000. It was filled with vulnerabilities. And a typical vulnerability is what I'm showing in the screen. So we're getting arguments from a GET request in the web interface. Then we are comparing this parameter in terms of its length to some maximum value. And if the max value is exceeded, that is, if the size of the buffer is exceeded, then an error flag is created, but the program doesn't stop at it, and it does copy the parameter as a whole into this buffer, regardless of its size. And this obviously results in data in the stack being rewritten, which may be exploited to run arbitrary code. It's so easy to trigger it. For example, we can send 1,000 letters A as a value of this parameter in order to crash the whole device, and the device will reboot. Let's look at another vulnerability, which is actually very similar to the one we have just discussed. However, this time the content of the parameter will be copied to a buffer which sits in global memory in the BSS section as opposed to the stack. Again, this vulnerability could potentially be used. In order to trigger it, it would be very rational to fuzz it with some relatively large value, hoping that something important will get overwritten. However, we send 1,000 letters A and nothing happens. Although we, or rather I, knew for a fact that there is important data sitting closer than 1,000 symbols, but I persisted. I plowed on. I sent 50,000 letters A and nothing happened. I sent 1,500,000, roughly 150 kilobytes. And this is when the switch started behaving weirdly. It logged me out of the web interface. It became sort of unresponsive. What do we usually do when the device doesn't behave well? Well, we reload it usually. Reloaded I did, but the switch would not turn on, which means I was left with a brick, initially worth $5,000. So it would reload eternally. I mean, I could press the reload button, but it would never start the boot cycle. So we had to dismantle it, and we found a COM port there. It actually even had a connector next to it. We connected to the COM port, and we found the following information. it turned out that it would start the booting process. It would write debugging information into this port. So it would start the loading process, it would start certain tasks, but then we would see that Telnet was listening on port 16705, as opposed to port 23, which is what it usually chooses. And SSH is also listening to the same port, which is A, very unusual, and B, we actually know that Telnet and SSH are not going to work fine on a single port. Also, we see a pretty high value in the enable some foot filter flag. So if we do a bit of math, if we transform these values into hexadecimal system, we will see that this will be the hex value. And 41 is actually equivalent to A, which means that 150,000 letters A that I sent over the web interface arrived here. Which means I was successful in rewriting it, not just the Telnet and SSH ports, but also something so important that the switch can no longer function. Naturally, the only thing we could do was to call Vladimir Nazarov, get our soldering iron, and actually connect a USB stick to it. So, what we could see in the operating system through the image of the operating system located on the flash drive was indeed so many A's in the operating system. So it turned out that all the data I wrote into the global memory was also written into the flash memory right away, which is a very weird choice design-wise, but here you go. That's what they did. And this is something that none of us expected. So everything was rewritten in the flash memory starting from the very beginning of the buffer. So you see symbols A followed by FFs in hexadecimal system. Now these FFs naturally mean the end of the flash memory segment. This means that we were able to rewrite the whole flash memory until the very end. Now, if we find place in the global memory for, say, auth data, authentication data, we will be able to see that it's 110,000 symbols, so 110,000 bytes away from the place where I started rewriting the buffer, exploiting this vulnerability. This is why I had issues with authentication, because all this authentication data, usernames, password hashes, access rights, they were all rewritten. We had trash written over them. And as we realized, even after authentication data, there was a lot of other important data regularly used by the firmware. And all this data was also written over. Naturally, we wanted to revive the switch. You will remember it cost $5,000. So we continued our research into the flash memory. And it turned out that the flash memory was used to store two configurations in binary form. One was overwritten with letters A for 52,000 bytes and another for 116,000 bytes. This happened because one of these configurations was the current one, while the previous one was a backup, so we could potentially restore to it. And as we analyzed the boot process, we realized the first thing it did was to try to apply the current configuration. If it fails, the system tries to apply the second configuration. And how will the firmware know if the configuration is any good? It looks for the checksum. You can see 87 in the screen. It is actually the number of the configuration because it has been overwritten 87 times, followed with 4 bytes. So if something goes wrong, if there is, say, a broken byte in the flash memory, they won't match. This will mean that the integrity of the configuration has been compromised and will need to boot using the backup configuration. However, due to an unfortunate sequence of events involving me rewriting configurations, it actually seemed okay to the firmware. So it actually calculated the checksum on the new configuration. So it would never switch to the second configuration, which would potentially work. So we changed the current configuration to the previous one. And we only had, like, the previous configuration we had, it was overwritten by like 52,000 symbols. So we were able to restart the switch and we were able to reset it to default. We were so happy to see it coming to life. You know, network function would work, interfaces were running just fine. Except for the web interface. The web interface continued to be glitchy. It was so bad it was nearly impossible to use it. And what saved us in this respect was that all the data of the web interface was cached. And we also had a copy of it. Because we were using the web pursuit toolset, and I had all this data in my cache. So I was able to go back to one of my previous calls, the one I used to trigger some defaults in the configuration dumps. So by sending this call so many times, I was able to arrive at the moment when the web interface was in working mode. And therefore, my call was performed, and default configuration was written on top of the current configuration. So the switch was restored back to normal. What are the conclusions I should make from this emotional situation? Well, first, there is always this possibility that you are going to break the device. So if this device is using some very weird architecture, save often. Actually, I would even make a stronger argument. If you have a live equipment, if you're working on site, do not fuzz it. Do not try doing anything fancy to it. Because if you are successful breaking it, chances are you won't escape unscathed, as I was lucky to. The vulnerability we have found is proof that an adversary should be able to do the same, to get persistence by compromising networking equipment, and a reboot will not help. You will need to replace your network equipment because nobody's really going to, work on the flash memory and perform this little dance that we had to perform. Let's look at another example. I've mentioned already that vendors very often implement undocumented features in their solutions. Let's consider here a smart electricity meter. We researched this one as we prepared for Positive Hack Days 8. This smart meter, I guess, was one of the smartest ones we could get our hands on. It had Telnet, it had WEP as well. So we can use the US command to actually study all the parameters of the command in question. And we can check, for example, what the consumption has been over the last day or last month. When we start reverse engineering the firmware, we shall see that this equipment is running on the Blackfin CPU architecture. Blackfin is quite exotic. It's also running on a real-time operating system called VDK, and they're using a network stack called Lightweight IP. Network stacks we discussed in more detail yesterday. The usage of this network stack made our life easier. Having downloaded this network stack, we have been able to quickly learn about the network functions being used there. And based on them, we were able to identify the handler of the US command. Then we follow the code of this routine, and we were able to find this, because of the US command, we were able to find the switch routine. And you can see a bunch of arguments here that US uses. Most of them actually were not used in the firmware itself. Actually, the arguments finish with plugs, with blanks. But interestingly, some of these arguments were not even shown in the help file, so to speak. Neither the manual nor the help command explained anything about them. Having analyzed these undocumented features, we realized that if we connect to the device and use a command like this, the device is going to issue a hexadecimal challenge. And if you study the firmware, you will find a way to decode it. So if you respond to this challenge with the right response, the one expected by the meter, the event log will be wiped together with all the settings and configs, and together with the information about total electricity consumption. That is, you revert it to near new state. Also, you can, if you know this challenge and you know the response, you can forget very conveniently to pay for electricity as long as you like. simply by resetting the smart meter from time to time. This is just an example of the kind of undocumented features it is so easy to find in so many devices. Now let's discuss the vulnerabilities that have surprised us, those that I'm calling atypical here. For example, a controller from one of the vendors had a GDB debugger embedded. The controller worked on VxWorks, but for some reason the developers have embedded this GDB debugger. Actually, I guess they wanted to use it to debug PLC programs. I guess they were trying to do good by the engineers, or to make the engineers happy. If such a debugger is there, obviously you need to activate it. You activate it using the engineering software, simply by pressing a button called Start Debugging. Naturally, we're able to discover it. And we realized that repeating the network exchange leading to the initialization of debug mode was no big deal. So if you initiate this exchange, the debugger will switch on port 2323, and you will be able to connect to it using all tools that you have. In the screenshot, you actually see how you can switch between the threads, for example. And obviously, you can read and write the memory. All debuggers enable you to do that. And since this was a VxWorks operating system, so there was no processor there, which means there was no distribution of memory between the CPU and other elements, as you will find in the traditional operating systems. In traditional operating systems, you cannot really rewrite memory of one process from another. This was no problem here. Memory rewrite was totally uninhibited there, simply because there was no division, so to speak, of memory. And also, this enabled remote code execution. Another interesting case is the case of eternal or endless update. This is what we saw on a number of different devices, but let's talk about protocol converters, RS-232 to Ethernet. And firmware updates could be triggered over UDP. So when the device got a special packet, it would switch to the update mode. In this update mode, it would simply wait for the new firmware, and it would stop functioning. The problem naturally was that if the firmware was not delivered, the device would stay like this forever. Even a power reset would not help. And since we did not have a legit firmware for this device, it actually entered this state forever. It was nothing to shed tears about. It was a cheap device, so we continue to happily break it apart. However, it is still illustrative. It shows, how a weird choice of architecture, this time update architecture, can lead to atypical issues. Now that we understand what to expect from developers, what to expect from firmware, Let's discuss the good practices. Firmware like this can have an unusual format. For example, it can be just, executable code in plain text, no imports, no function names. So if we're considering a network vector, it should be useful for us to know where network functions are located so that, we can see which particular ports it is listening on, how it parses the data it receives, and so on. Because this knowledge will enable us to identify new vulnerabilities. One of the ways of doing that is to look for the strings in the firmware for information about network interaction. That is, to look for network send, receive, and similar operands or strings. As you can see, this is exactly what worked for us here. We discovered in this firmware, and it's actually the firmware we tried before as we learned how to upload firmware to IDE. So this is how we found those strings, and when we Googled them, it turned out they were functions from the traditional libc, and they were stir error and similar functions. Based on this, we should be able to use crosslinks that we successfully restored as we loaded the firmware. We should be able to see this PER function until it's called and see what network functions it invokes. Another way of looking for networking functions involves looking for prototypes. Let's consider it using the socket function as an example. It is very well known that socket function, belonging in the family of Berkeley sockets, which is the one that is used pretty much everywhere, operates with 3 arguments, or takes 3 arguments. For networking sockets, the first argument will be 2, IF, INET. The second argument will be either 1, 2, or 3, representing, respectively, sockstream, datagram, and raw sockets. Stream is obviously TCP, while datagram should be FTP. And third argument will be either 1, 2, 6, or 17, representing ICMP, TCP, or UDP protocols. And if we look real hard in the firmware, functions that take such 3 arguments, we will be able to find a function like the one I'm showing in the screenshot. We'll see, for example, that R4 is argument 1, and it does have the value of 2. R6 is the third argument. So it sends 11, but this is actually 17 in a different system. In the binary system, in the decimal system, I'm sorry. And since this is Super H processor and has JLL slots, so before switch to socket is made, argument R4 will accept, R5 will accept the value from R4. And this will also be constant 2, which actually stands for socket digram. So this is how we can easily decipher all the networking interaction here. We can also use a variation on this approach and look for constants. What kind of constants can we find there? Well, this will be port numbers, for example, or packet signatures. For example, they may contain some magic numbers. And some equipment, PLC equipment, for example, may well be using some hard-coded IP addresses from hard-coded subnets. Using this approach, we can also locate a bunch of networking functions, as shown in the screen. You will see, for example, hard-coded IP address, 192.168.136.2. It's very easy to find it simply by looking for the bytes. And chances are it is going to lead us to some network node. We can also see here in the screen a constant. It could have been a different IP address, I realize now, maybe A2. So we can see a constant of 6,000 here. This constant is in line with the port number. As we can see later, it goes into the bind function, and it is also handled by the UDP socket function. However, not every firmware operates with unnamed functions. Sometimes the firmware itself helps us a lot, meaning that we won't have to exert that much effort. I'm referring to cases where the firmware itself includes symbols such as names for variables and names for functions. This is what often happens to VxWorks operating system. When you're working with VxWorks, you will discover that many functions come with their names attached. This is what you can see in the screenshot. It does run on VxWorks. That's what it says here, VxWorks 6.6, making it not the cutting-edge version. If we analyze the individual strings here, we have seen quite a number of lines here which look like names of functions or called variables. So the only thing remaining is identifying what we can do about it. So if we take an address of a particular line and we'll look for it in the firmware in binary coding, we will see this address being used, and it's used in the data section. There we find a pointer to this particular line and also another one. And there are also pointers there to this global variable. So a variable here is called functask stack A in the address you see in the left. Next, we will need to find a function from our standalone init. This function, use our standalone init. This function is responsible for initialization of individual components. In particular, it will populate this symbol table. And the symbol table is needed in order for the command line of this operating system. Functions could be called by the name. If you study it closely, you will see that this function does indeed invoke the symbol table that we found previously. Actually, that's it. Here you see the function name, the variable name, the address of the function or variable, and additional data. A table like this can contain dozens of thousands of functions, which means that we need to automate the process of renaming those functions. To get there, we may simply produce some Python script. For example, this script shows that we start, with the symbol table. Then we calculate total number of symbols. And since one element of this table has the size of 20 bytes, we use it as an argument, and the rest is pretty easy. So we iterate throughout all the symbols. Next, we take name pointers, pointers to functions. We take flags as well. We create a structure. And then data is aligned with the new structure. After that, we should be able to see in IDE Pro that many functions will have names. It should be very clear that this is making our life so much easier. This will be some of the last slides in the technical part of today's presentation, and these slides will contain information that may help you refresh and better remember what we have already discussed. My colleagues yesterday sent my way an interesting publication covering this issue or this subject of industrial equipment security. It's, let me put it differently. Vulnerabilities of industrial devices are very prevalent. They can be found in so many firmware units in the world. And what we are covering here is the classification of various code vulnerabilities, such as incomplete faults or alarms handling. For example, if malicious code can disable or silence certain alarms, the operator will not even learn of a malfunction, or say will not learn that a certain indicator has already surpassed a threshold, which may actually lead to technological issues, if not catastrophes. Lack of instructions. When a particular scenario or a particular behavior is simply not described in the code. This is also a vulnerability, because the PLC may totally misreact if it is not kind of hard-coded to behave in a particular manner. Hard-coded values. Actually, we're still seeing some hard-coded passwords in industrial software and hardware. Other parameters can be hard-coded, and it is often a bad idea. Racing conditions. Discovering them can be quite difficult, but they can still be detected and exploited. At the end of my list, you should be able to see something that we consider quite interesting. That is infinite loops. So a device can simply freeze as it is so busy with an infinite loop. And the classical fatal faults. So certain faults may actually result in the crash of the PLC software or the operating system as a whole. Naturally, such faults should better be identified and debugged by the developers. More detailed exploration of PLC's vulnerabilities. That does not require reverse engineering. Would include, for example, using like escalating privileges on a high level, like in VxWorks. PC bind was a very well-known vulnerability. And the consoles used for managing PLCs can also be attacked. Sometimes devices themselves are not password protected. So it may easily happen that the PLC, for example, is protected apparently with password checking, but a particular engineer may decide that it's not convenient to keep passwords in bind, and he will simply disable password checking. Now, as regards to HMI vulnerabilities, some attacks here will seem very trivial, such as SQL injections based on web applications or for HMIs based on web applications. Obviously, these are not exclusive to web applications. Even in binary applications that we saw, say, in databases, very trivial SQL injections could be found. Another popular vector is a deception attack. For example, you can spoof network traffic or use some malicious code in the operator's workstation. You can change the way certain parameters are displayed, and that way the operator will continue thinking everything is fine while something horrible is happening. We can also consider network vulnerabilities. ARP spoofing is something that everybody knows. There are other things you can do in order to undermine proper network interaction, or you can modify packets. Network equipment attacks also fall in this category. I'll take, for example, the switch I mentioned previously today, the industrial switch. So it had a vulnerability in the routing protocol stack. In particular, it was a vulnerable version of the OSPF library. So a particular OSPF query would freeze and then reload the switch. And if an adversary is persistent in the network, he can easily continue those attacks for as long as he chooses. Know the line with backdoors and holes in network perimeters? What happens quite often is that although, all bolts should be tightened and everything should be adequately secure, Very often, people leave certain holes for convenience, and then pen testers or adversaries can easily find these holes and abuse them. I realize the time allocated to this speech is drawing to a close. So by the end, at the end of this section, I would love to announce what's coming next at 7 p.m. I will be happy to take your questions. Some questions certainly should be submitted via the chat. Also, you can contact me directly using email and Twitter. Some people have already contacted me, and it has been a pleasure. In conclusion of this part, let me say that your feedback will be highly appreciated. Actually, you've got a great opportunity of influencing the future of this course. All it takes is just following the link currently shown in the slide. And if you can fill the form out and share your impressions, we will be very happy. Actually, this is the most important thing you can do for us, because we have developed this course in order to train people, and it is actually a pretty challenging subject. It's important for us to understand if we have been marginally successful. We'd love to hear from you what you like, what you don't like. So please contact me directly via Twitter or email if you have any comments or critique or whatever. This is where I would love to announce this section over, but please stay tuned. See you at 7 p.m. to take your questions. Thank you very much. Thank you, Slava. It has been very good. I am going to copy this link in the chat so that people can actually use it. Thank you very much. See you in an hour, or a bit more than an hour, 7 p.m. Moscow time. Thank you very much.